Thank you everyone for making it, and early on the second day of DevCon. All right. Perfect. So yeah, I'll just do a quick introduction for the day. I think nothing too crazy to talk about to kick things off. But I want to warm us up a little bit in thinking about intents and chain abstraction. I think at OneBalance, we sort of picked up on the concept of resource locks and started picturing and imagining what the crypto and Web3 and Ethereum ecosystem will look like once we have thousands and then quickly millions of different rollups and chains. And trying to think through what is the way to create a really great user experience in that world where you just get more and more fragmentation. And the concept of a resource lock became very fundamental to the way that we envision this future. But it also leads to the question, what the fuck is it? Because resource lock is a new thing that isn't a part of the stack today and a fundamental part of it. So we're going to play a little game, which is this a resource lock? And we will try to build some intuition for what a resource lock actually is. So, okay, this is a deposit screen on Binance. You're welcome to send me money if you want. But the question is this a resource lock? Is like an on-chain deposit into Binance a resource lock? And so let's just do a show of hands. We're all close here. We all know each other. We're willing to do like these little pop-up quiz. Is this a resource lock? If it is, put your hand up. Okay. Decent chunk of people that call it a resource lock. What about this? Is the Lightning Network a resource lock? Okay, a different set of people, interesting, okay. Is Gnosis Pay, are these like payment cards resource locks? Still a lot of hands, nice. Well, we're defining it through examples. Magic Spend Plus Plus, is that a resource lock? A couple fewer hands actually. Interesting. The Compact is something new that our friend Zero Age put together. Is that resource lock? It says it right here. Okay, so definition of resource lock. Super simple. I think resource lock is just a guarantee over state. And the specific guarantee that it is that you have some level of confidence over the finality of this state, meaning it's not going to get reorged. What you see is what you get. It's going to be in the chain forever and ever and never going to change. The other one is that there's equivocation protection, which is synonymous with double spend protection. So that state update or that state request that's being provided cannot be updated by the user in a unilateral way. And so what does this mean? It means that you can rely on the state, even though it's not finalized per se in the chain, you can rely on that being the way that the world is, and you can take some actions based off of this. So it's a credible state. Then what is an intent? So at least the definition that I want to share with you guys with what intent is, and maybe the Anoma people will like bonk me over the head later today over any of these definitions because they're much more rigorous than I am. But an intent is just input state and output state. So you input something into a request, and then you define what the output of that request is. And you sort of have your intention as opposed to a transaction that defines the input request and the execution. And then the next one is, okay, what is an intent plus a resource lock? I was very tempted to call it a turbo intent, but instead I just went with cross-chain intent, which is what do you actually achieve by combining the two is you can bring an intent-based system and have it reliably execute in a multi-chain setting with the guarantees of finality on the source chain, and sort of the benefits that you get from the execution of the intent. Now, you still require some kind of proof mechanism to show that the execution happened correctly, which is why you also need to add an oracle into this. I think a lot of the chain abstraction sort of world can be summarized by this last line. When you're doing operations in a multi-chain setting, you need to have some confidence on the source chain that you're getting finality. You need to have some way of expressing the message that you want to carry to the destination chain, and they need to have some kind of proof that the execution on the destination chain occurred the way that that you wanted. So this last line really, in my perspective, summarizes what chain abstraction is. Okay. This is, I think, the key insight that led to me founding OneBalance and really being quite bullish on the concept of resource locks, which is it sort of breaks out of a paradigm of that everyone has had when thinking about interop in an asynchronous system. I think a lot of the design, if you think about like shared sequencing or even database design, distributed database design, it thinks about how do you guarantee composability or atomicity in an asynchronous setting. And the sort of intent plus resource lock approach, instead of guaranteeing it, it purely incentivizes it. And so it creates a, I guess in MEV terminology, you could say a bribe or just an incentive for some counterparty to actually enforce that atomicity on behalf of the system that they're operating against. So you're shifting what is sort of a difficult guarantee to give, given the asynchrony, into an economic guarantee that's provided by a specialized party that can take that risk, aka solvers. And so what resource locks and intent sort of enable you to do is achieve sort of the holy grail of asynchronous interoperability, which is atomic execution, without actually solving the computer science problem. And so you're adding a market, you're adding crypto economics on top of this problem, and you're all of a sudden achieving the outcome that you want. And so we love to do this in blockchains, and coming to this insight is, I think, the key one in recognizing that resource locks are somewhat inevitable in a multi-chain future. I want to talk a bit about sort of resource locks versus other types of interop approaches. I think the first one is the canonical bridge. And when you talk about L2 to L2 interoperability, this is like really the slowest way to do it. This means like you're passing a message from an L2 down through the proof system to the L1, and then back up through the bridge in the other L2. And so the bridging time for that is whatever the fraud-proof window is for an optimistic rollup, or the proving window is for a ZK rollup. And so it's like up to 7 days, so very slow. You have arbitrary message passing bridges, which are like, okay, well, maybe you don't need to wait through the entire finality period. Maybe you can have some gadget that allows you to do this a little bit faster, and you still have to wait for the finality on the source chain, but maybe you're willing to take a little bit more risk on the finality and pass a message. And so actually, if we look to, I think a good example of what like a message bridge speed is if you look at the deposit time on a centralized exchange. So whether it's Coinbase or Binance, depending on the chain that you're depositing from, they're going to wait for like a certain number of confirmations. And that's like a good representation of what the speed of message passage bridges can be. Then we have our fast bridges or intent bridges, which start to introduce the concept of solvers and resource lock. Now, I create a distinction between just an intent bridge versus a resource lock bridge, because the intent bridge still relies on the execution speed on the source chain to provide the guarantee of non-equivocation. However, once you have a resource lock that is not tied to execution on the source chain, you're not tied to actually the block times of the source chain for providing these guarantees. You can have the non-equivocation and the finality guarantees be enforced much faster. And so that's why the resource lock bridges end up being the fastest in sort of a asynchronous setting. I spent a lot of this is the question that I've been asking everyone this week. It's what is the role of resource locks within a future where you have native interop built into all of these L2 clusters? So whether it's Ag layer or Elastic building sort of a proof aggregation layer for interop, or you have on the Optimism and Arbitrum side, you have Superchain, and then you have Arbitrum clusters that are promising native interop. What is the role of cross-chain intents and resource locks in each of these? And I don't think that this is fully answered yet because no one really knows, and it hasn't been shipped, what like clustered interop actually is. It's more like an idea. But at least from like the research perspective, these are the fundamental trade-offs that I've been able to sort of identify. So within the ZK stack, message passing is always going to be constrained by the proving speed. And so there's this ephemeris concept of a real-time proof and real-time proving that is sort of the holy grail. But right now, the proof speed is, you could say, like 5-10 minutes. And so the fastest message passing that you can have within this native interop for atomic execution is going to be the proving speed. And then the second point is, even if you have 100% instant real-time proofs, you're still dependent on the L1 finality for prevention of reorgs. So if your L2 ZK rollup checks in its proof to the L1, but then the L1 reorgs, the L2 can just produce a completely different set of transactions, which means that if you have any other L2 within this cluster that's listening to that message, that will also be forced to reorg. And so this is sort of the problem called cascading reorgs within the L2 interop space. And as far as I can tell, that problem is fairly fundamental, unless you have rollups all check in at the same rate within the same L1 blocks, such that they all reorg together by default. And so, yeah, these two sort of problems I think are unsolved in the ZK interop space. Now, in the optimistic interop space, the answer to interop there is like a super sequencer, which has its own trade-offs. So when you build a interop into optimistic rollups, you basically require all of these rollups to behave in exactly the same way. So they have to have the same security model, basically be run on the same machine, such that you can have the message passing from one rollup to the other. One of the challenges that we lost the slides. One of the challenges that you encounter when you have interop like this at the level of the optimistic rollups is you. Cool. Sorry about that. If you have a single sequencer that's producing the blocks for both rollups, you have exactly the same security assumptions. So let's just take like an example. You're within the Superchain environment, and I launch my own rollup, and it's really, really shitty. And all it is like a game, and I run my own sequencer. I'm like, okay, great. I want to leverage the liquidity that's inside of the base rollup. And I believe that I'm a part of the Superchain, and therefore it's as easy as sending a message to the base rollup, doing a trade, and then bringing back the execution to my game. In reality, what happens is that if I send this message, but then my rollup goes off or has a reorg or whatever it is, I can force trigger a reorg within the base rollup if it's entertaining the message that I'm sending, which means that every single rollup is going to have to define sort of a whitelisted set of other rollups that will accept messages from, and like very, very heavily guard those integrations, because they can arbitrarily trigger reorgs within their own rollups. And so, what it requires is the shared sequencer, the shared security assumptions, and then it also requires foregoing sovereignty, such that like I cannot just push arbitrary upgrades to my rollup anymore, because if I do, it will violate the security assumption of every other rollup that I'm interoperating with. And so everything becomes sort of a shared upgrade mechanism, and then it really just behaves as another chain. So those are the trade-offs there. Cross-chain intents also have trade-offs, and this is mostly about capacity constraints on the liquidity. If you have millions of rollups, it's difficult to find solvers that are going to be willing to put millions of dollars on all these millions of rollups, and so you're always going to have to, have sort of a trail amount of inventory across all of these different places and transact in smaller amounts typically. And then there's a bit of a black box reliability problem. And this is the same thing as any market-based system where you have some specialized actor that's providing the liquidity. They have a better view of the market. They have more information. They can just turn off their system at any time if their risk parameter go out of whack. And so you have this problem of when you need the liquidity the most, the liquidity evaporates. And so those are sort of the trade-offs of these intent-based systems. Okay. We'll keep trying to fix the slides. My next one was maybe the first thing that's really OneBalance related, which is what are our actual products. We're building two things. One is a chain abstraction toolkit, and this is really oriented towards apps and wallets. And this is sort of everything that you need to create a chain-free, bridge-free, and gas-free user experience. And then the second, we have an example demo app that you can use that does cross-chain swaps in a chain abstracted way. And then the second system that we're building, or product that we're building, is resource locks as a service. So again, we're very bullish on this concept of resource locks, and we believe they can turbocharge essentially any infrastructure. And so this product is for infrastructure players and issuers to be able to introduce resource lock into their systems. And then we launched just last week sort of an example of what a resource lock on top of a token can do, which we call teleport. So you wrap your token once, and then you can instantly mint it and bring it to any other chain using resource locks. So yeah, that covers everything that I wanted to talk about today, and I'm excited to dive into all of this some more with you guys throughout the day. Let me know if you have any questions. Yes, sir.
Do you have a white paper?
Soon, TM. Do we have a white paper? Yes.
How does this help wallets monetize their order flow over what they're doing today?
That's a great question. So honestly, order flow monetization is probably the main thing that I've thought about over the past 3 years. And I gave a presentation in 2021 that says order flow has a solution, which was really talking about the trade-offs when you're designing things like order flow auctions, right? So you have this sort of trade-off between speed, reliability, and price. And when you are building these things, because you want to capture some kind of MEV value or something else, you have to pick some trade-off in this trade-off space. I think what we will see is each system that builds intent-based bridging is going to pick some point in this trade-off space, and won't necessarily look to monetize MEV to start or sell the order flow. But what I do expect is going to be helpful to apps when you do chain abstraction is that you have opportunities for new ways to do accounting for fee taking. So instead of having the Ethereum transaction object, right, that has gas fees embedded within the message that you're signing and then doing the execution on chain, what you're actually surfacing to the user is just requested state transition plus a fee. And in the sort of gas abstraction world, that fee encompasses everything that you're paying for. So it encompasses the fee for the gas on the source chain, the fee for the gas on the destination chain, the fee that's being taken by the solver for providing the execution, and you can also bake into here some fee that's taken by the application or the interface for providing a service. And so I think that chain abstraction concept in general also offers fee abstraction, which gives an opportunity for apps to add a fee as sort of a bump on gas price that they're submitting. I think that that's going to be the first way for apps to monetize. And I think that's probably the best way for them to do so, rather than through MEV or anything else. Okay, cool. Thank you, everyone.